Good morning or good evening, wherever you are. We are going to discuss today our introductory lecture on the data analytics course. And what we're going to talk is about a series of popular views, mainly on the epidemic of data analytic discussions that there are in the press and in business currently. And this particular discussion will be mainly on data analytics, not in data analytics applied to audit, which we call audit analytics. And the reason for that is that it's interesting to see what business is doing in data analytics in order to understand a little bit what can be done in audit analytics. During this course, not this lecture, you're going to have the opportunity to see a lot of the work that we're performing at the Cal Lab, emphasizing using some of these techniques and some techniques that are not really currently discussed in the press in specifically the audit domain. I want to call your attention to a couple of books that are popular press books that might be interesting to be read. And first is this book by George Friedman called The Next 100 Years. And I find it interesting, but not admirably interesting. It talks about a lot of data analysis type of issues and some predictions about technology. Now, this actually is a more interesting book. It's by a guy called Ian Ayres. He's a professor of law at Yale. And he basically talks about the advantages of large data analytics and gives certain very interesting examples that are very good to call your attention. And I am going to actually discuss some of these examples from Ayres' book. The third one is a little bit closer to the accounting area. Tom Davenport is an accounting professor, but he also really doesn't talk too much about accounting. It's mainly about data analytics. If you had to spend money, I would suggest that you buy the supercrunchers first, the competing analytics second. Third one is this book, Future of Analytics, has some interesting insights. It's not tremendously insightful in my opinion. If you go into Amazon and look for data analytics or big data, etc., you're going to find a lot of offerings these days. Okay, the first thing, the question is, we have to discuss and think a little bit about is on learning and on usage of data and on modeling, what are the real interface or what are the differences between humans and machines? And what did we know today from the behavioral science on this area? And this is out of the supercrunchers book. Supercrunchers are much more accurate than traditional experts in terms of prediction. Neil and Grove completed a meta-analysis of 136 man versus machine studies. In only 8 of the 136 studies was expert prediction found to be appreciably more accurate than statistical prediction. Now, what is meta-analysis? Is analysis of analysis. What does that mean? Is that they picked up these studies, they didn't perform the studies, they compared the results of the studies. And actually, when you are trying to get a wider view of a particular phenomenon and try to understand better, and there are a lot of studies, you do a meta-analysis. In the medical field, it's very, very common that you pick up many, many studies, and you look at the results and see if there are commonalities or they are antagonistic in results, and etc. And obviously, if you find things that are similar in the many results, you believe more that particular finding. And this particular finding says that expert prediction more appreciable, more accurate than statistical prediction. So basically what is saying is that if a person is an expert, as opposed to a machine, he predicts better. Now, that raises a lot of question of what is an expert, what domains they can do, etc., etc. Overall, when asked to make a binary prediction, the average expert in wildly diverse fields got it right 66.5%. However, supercrunchers had a success rate that is 73.2% according to results from above analysis. So I have to revert myself. In only 8 of the 136 studies was expert prediction found to be appreciably more accurate than statistical prediction. So what does it mean? That in 128 studies, machines were better than humans, and humans were only better in 8. Now, you have to be careful drawing these conclusions because, as it says here, wildly different fields have wildly different behavior. Now, this is out of the behavioral science. Human mind tends to give too much weight to unusual events. So if something systematically out of your domain happens, you give it a lot of weight, even if it's just an anomaly. For example, people systematically overestimate the probability of newsworthy death, such as murder, and underestimate the probability of more common cause of death. That's a pretty common type of thing, and there has been a whole set of studies looking at fears and risks. And in fears and risks, you typically are afraid of things that are not so dangerous. For example, one of the examples that is used is the example of people are very afraid of having guns in their household for their children. On the other hand, they don't think too much about the swimming pool. The probability of a child dying of a gun-inflicted wound is 1/10 of the probability of they drowning on the pool that you have in your house. So this kind of illustrates how there is kind of linkage, there is kind of overweighting of unusual events. Humans tend to cling to our mistaken beliefs, so we discount this confirming evidence and focus instead of evidence that supports our pre-existing beliefs. So very often, you just stick to an idea even if the evidence goes against it. In sharply contrast, superconscious models have no emotional commitment to the prior predictions. So going back into these 2 slides, this basically indicates that in the selected 136 studies, large majority of the studies, unbiased machine prediction was better than human prediction. And the reason for that is basically some kind of cognitive bias on newsworthy events and on pre-existing beliefs. Now, in audit and in audit analytics, in particularly in the past, most of analytical review work was basically on ratio analysis. And in ratio analysis, you basically calculated the ratios of different things in financial statements, and then you try to look at the trending, see if that particular ratio was somewhat different from the industry ratio, something reasonably simple like that. There hasn't been too many more advanced analytic usages except in the recent years. Now, the granddaddy of analytic methods besides ratio analysis was regression analysis. And they use regression analysis. Deloitte has been using their STAR package for over 20 years, developed originally by Stringer and Trevor, who works with us, and has been reasonably successful but not adopted widely. Now, here out of the different examples, we're going to talk about regression applied in other fields with reasonably good success. Okay? This is actually an example out of one of the books that we mentioned before. This Mr. Aschenfelder, an economist professor, I said that he loves wine. He crunched numbers to assess the quality of Bordeaux wines. Low levels of harvest rain and high average summer temperatures produced great wines. And what he did, he created multivariate regression. What is a a multivariate regression is a regression whereby there is a dependent variable and there is a set of different variables, that's why it's called multivariate, that try to explain this particular event. And the way you do this is that you have historical numbers for your dependent and for your independent variables, and you finish up kind of running these least square regressions and coming up with these parameters. It's a very robust technology. Regression numbers are very resistant to variations and to discontinuities and to aberrations in the distributions. Now, this is just kind of a light example for you to get a feeling for what this thing is. We are going to, in this course, talk much more about regression in general. But for you, mathematically, this is a dependent variable. These are independent variables that you have some reason to think that affect this variable. And you basically build yourself a little matrix, say this is a dependent variable, this is what happened in the past independent variable. And the formula basically tries to extrapolate a line into there. And there are the parameters that determine the weight. And it doesn't matter what kind of variable that you use here, as far as it's a continuous variable, if it's normalized or not normalized, this particular variable here adjusts for the normalization that you did here. But in general, what you need to think about is that this is just a linear formula in which this thing here is explained by this thing here. And the variables that they use here is rainfall, average growing season temperature, and harvest rainfall. The rationale was associated with what they knew about the wine. Let's talk a bit about collaborative filters. Internet retailers keep tracking of customer behavior, cluster them into groups, and recommend products to customers according to historical preference. For example, Netflix recommends different movies to different customers. As a result, more than 90% of the titles in its 550,000 movie catalog, which is much bigger now, are entered at least monthly. Pandora.com helps users to find music that they have never heard of, and that's done by association. MSNBC uses a cookie to keep track of 16 articles users have most recently read, and uses automated text analysis to predict the news users want to read. It's the magic of the wisdom of the crowds. Another example, there are many other examples. If you use Amazon, they always send you this little note saying, people that bought this book also bought this book. And they obviously know that those propositions usually work. And they get a lot of sales by telling association. And they do even better when they have a whole larger profile of the things that you buy. And back to eHarmony. eHarmony tries to find out what kind of person you are and then matches you with others who the data say are most compatible. 4 is the step to find the right match. Complete our relationship questionnaire and get your free what? Review your selected high compatibility matches free. Pick the plan that best suits you when you are ready to communicate. Get to know your matches at your own pace and start dating. Notice that the first 2 steps, which are to get you in, is free. The last 2 steps you already have to pay to get in contact with the person. Again, remember what I mentioned before. eHarmony has a regression with 29 or 28 variables. Sounds a little bit too much to really good explanation. Probably a few of them do it all. Customer-oriented supercrunching. Forecast the trend of particular airline fares for customers in Greece. 115 different factors are used. Historic price and patterns and other factors impact demand and supply tickets are included. There's actually a website called Faircast, not Forecast, but Faircast. And you can go in there and have a look, see what if you're going to go to San Francisco, and the fares are very high now, if they're going to go up or down. Zillow.com predicts home prices to help both buyers and sellers price their homes. Dust Network crunches data on the speed of 500,000 commercial vehicles to predict traffic jams. Ganni is working on personalized shopping, etc., etc., etc. Okay, now let's just recap for a second. We started by looking at around 4 different titles that talk about this idea, the generic idea of data crunching. I said that super crunchers and computer analytics are probably the best ones to be read. And then we drew examples out of that. And we first talk a little bit about data analytics versus audit analytics. And what we said is that data analytics are the field that is being used all over the world in this moment, particularly in the advanced data-enriched businesses. And audit analytics will be an application of this into the audit domain. And that today we are going to speak mostly about data analytics, and the rest of the course we're going to talk mainly about audit analytics. The second thing we discussed here was humans versus computers. And what we basically concluded in a meta-study that statistical models are a little bit more consistent. They're more consistent in predicting facts than human experts. And of course, there is a whole range of human expertise, and you would expect that the better expert to have better ratios than the less good experts. Same thing with models. You would expect some models to be better than the others, and the good modeler will be able to get better predictions. I would love to have seen that same meta-study looking at comparing humans and machines decision-making, have a look at comparison between different machine prediction models and what's good, what's bad on that. Then we talked a little bit about regression analysis and the applications in regression analysis. The biggest one that we discussed more was on prediction of wine prices, Bordeaux wines, and on the prediction of baseball results. And both of those humans frowned and snickered and humiliated the statisticians trying to make the predictions, but at the end, both in wines and in baseball, there is a whole technocratic school of analysis that actually has pretty much dominated the field in the recent years. There is a whole field of wine price prediction, and there is a journal, there is a newsletter, etc., etc. And in baseball, it has been pretty much vindicated that statistical analysis is very useful for baseball, and most teams today have experts in statistical analysis looking at what they are doing. Now let's talk a little bit about randomization. Select a sample for experiment with a flip of a coin. Example, Cap 1 learned that simply adding a photo of a smiling woman in the corner of the solicitation letter raised the response rate of male customers. If it randomly divided customers in 2 groups and sent them solicitation letters with or without the picture. How do we know that that picture that caused a high response rate? This is what we ask. And obviously, a controlled experiment is an experiment that you try to create all the other conditions, to keep the other conditions set as variables without changing, and you have one variable that you measure. And the larger the sample that you get, and you compare the 2 effects, which are 2 effects really, you will have a more conclusive result. Okay, and there are ways to improve this randomization by matching pairs or doing some other ways. But the whole idea would be is that you use the internet, you use this kind of massive user basis of particular user interaction and create the effects there. In this case, put the picture of a smiling woman there and see if it makes a difference. Now, things get more complicated if you put 2, 3, 4, 5 effects to compare at the same time. There are statistical ways to try to pull them up aside, but the simple test one against the other is usually very powerful. And the one thing that you have to be careful is that the groups are really randomized. They are not biased. You compare a school, let's say a religious school, to a public school, and then you think that those populations are the same. They might not be. Okay, and that's the kind of thing that you want to be. You want to try to keep things reasonably well balanced. Okay, so continue randomization. And so basically you can use the web to basically pick up, want to know whether a web page design works better than other, automatic assessor software, so when people click on site, either one page or the other will be sent at random. The software will tell you in real time which pages get more clicks to which generate, and which generates more purchases. Very interesting. The thing to be wary about this, to be concerned about this, is are the people having access really randomized, or there is a systematic bias into it. When does randomization does not work? Think about this topic. Do longer sentences increase or decrease the chance that the prisoner will commit another crime? You cannot randomly select criminals and put them into two groups and then sentence them longer and shorter. Solution: use a pre-existing randomization. It is possible that judges with a district are seeing the same kinds of cases. Some judges tend to sentence longer and some tend to sentence shorter for the same criminal. This from the same crime. This disparities give a powerful way to measure whether longer sentences increase or decrease recidivism. There are many things that cannot be randomized, and obviously you have to worry about pseudo-randomization and et cetera, but in general, many of these problems don't occur for simple things that you are doing. Strengths and drawbacks of a database study, a medicine case. Database study has many advantages. Database study can discover rules and relations that are not being discovered by traditional study. For example, Don Berwick discovered that simply elevating the head of a hospital bed and frequently cleaning the patient's mouth substantially reduced the chances of infection. Data analysis with technology can dramatically increase the speed of innovation. Example, the practice of medicine before EBR, evidence-based medicine, movement has shackled with an extremely slow and inefficient mechanism for disseminating medical results. EBM has shortened the time it takes to disseminate important results. Information retrieval of medicine changes the medical mechanism by which patients can affect what their physicians do. Many patients go to sites like Mediline to figure out what might be ailing them before seeing doctors. EBM gives doctors for the first time the chance to engage in real-time epidemiology. The diagnostic software Isabel tells doctors that an hour ago in the 4th floor of the hospital, a patient was admitted who had similar features of infection and blisters. Very, very interesting possibilities posed by technology based in hospitals if these technologies are enabled. Collecting data of all patients, having this data in real time, being able to have analysis on top of this data, and have the analysis enabled in real time to be able to use this information. I just wanted to advance something here in the area of auditing. We have recently been talked a lot about changing a little bit the view of auditing. And they usually say the auditor is the general that comes in after the battle and shoots the wounded. And why do they say that? Because auditing is by definition, in current ways of thinking, a retroactive type of science whereby you look at the past and find faults with it and then deal with current employees with the faults of that particular fact. with the advent of technologies like real-time monitoring of hospitals, databases, models associated, et cetera, we can do what we call the proactive audit as opposed to the retroactive audit. And actually the word we typically use is proactive audit to look into the future, and we have basically two branches of the proactive audit. The predictive audit, and then we have what we call the preventive audit. And what we call the preventive audit wouldn't be called in old days an audit. It's a different kind of thing. They would maybe call it a control. But in the proactive audit, we develop models of what should happen. And then we compare with what actually happened and create new forms of audit evidence, which is comparing models with actuals, and if the actual is very different from the prediction, you might have an aberration. Now, if you have a real good forensic model to predict the future, forensic what? What does it mean? It's a model that you use past data, like in the example of baseball or wine, of what happened in the past, and you manage to predict reasonably future, like betting averages, price of Bordeaux, or what would be the financial results of a particular firm in a certain account, like cash or receivables or etc. If you are really good in predicting that, you might use that in other forms. For example, if you are really good in predicting that a particular transaction was fallacious, was fraudulent, meaning you have extraction tools that apply models to it and bring out a very small subsample of positives that you pretty much know that they are fraudulent or have a high probability of being fraudulent, why would you allow the transaction to be executed? You can, at that moment, before the transaction is actually processed, apply your models, see if there is a low probability of fraud, let it go. If there is a high probability of fraud, you stop it, have a human examine it, or have an additional process examine it, and then you execute it or not execute it. Or even use the technology we have been developing, which Professor Kogan has been developing, which is automatic correction of errors. So, in the medical example that we're talking here, they were predicting, they are identifying infections. How they were identifying infections? By comparing data that in the different places of the hospital was occurring, and if the same kind of symptoms happened, and happened out of the usual amount of happening, you might have a problem. This is very similar to, this is the pattern of a particular type of fraud, and this new transaction that just came in looks like that pattern. Now, if you have a wire transfer case whereby companies paying their vendors and other people to electronic wire transfer, and the particular wire shows up with a lot of the parameters of a fraudulent transaction, why execute the wire, send money to Switzerland that you can never recover? Stop. So that's what we call the predictive audit, or in this case, the proactive audit. And the proactive audit divides into predictive, that you only use the data to compare with actuals, or the preventive audit, where you stop work. Later in this course, we are going to actually have Sidi Pan Fukai Kangawal. She has a terrible name to say. Sidi Pan talk about her dissertation, which is called Predictive Audit, and she is going to talk about some of the analysis she did with data of a large bank. Back to this, the diagnostic software. Isabel tells doctors that an hour ago on the 4th floor, the hospital patient was admitted had similar features of infection and business. Very analogous to what we're talking. Drawbacks. Some problems remain in database studies. Some studies don't ask the right question to control sufficient variables. Example, a study concluded that excessive caffeine consumption increased the risk of heart disease without controlling for whether the patients in the study smoked. And if I recall correctly, the fact was there that that there was a high correlation between smoking and heart disease. and it wasn't really the caffeine that determined, it was really the smoking that was the major motivating factor. There is too much evidence-based information and individual practitioners to reasonably absorb. On coronary heart disease alone, there are more than 3,600 statistical articles published each year, especially who wants to read more than 10 articles every day, especially who wants to read more than 10 articles every day, includes weekends. So what he's saying, the wording here is not very good. In order to keep yourself up to date with coronary heart disease in all articles, you would have to read 10 articles a day. Sometimes it's impossible to control the variables. The evidence-based medicine movement has had the impertinence to ask doctors to change what they do with their time. And again, just reminding you what we talked in the beginning here is humans and machines. Humans are imperfect processors of information, and it's possible that the sources of evidence or the reaction to evidence that a doctor has is not really statistically the best usage of the time because they were too influenced by a particular abnormal event. Drawbacks of database analysis. Statistical procedure cannot estimate the causal impact of a rare event, like a broken leg, because there simply aren't enough data concerning them to make a credible estimate. There is no sample for basis. Solution combine both. In several studies, the most accurate way to exploit fiduciary expertise is to merely add expert evaluation as an additional factor in statistical algorithms. I can tell you a little bit about my personal experience and our first continuous auditing project that we did at AT&T. We actually used extensive amount of auditor judgment. We created rules based on what internal auditors thought that was a problem with that particular billing system that we were dealing, and use those rules to extract data. Once there was a larger set of data available for those type of phenomena, we started creating them statistically, or we incorporated a mix of statistical rules with the auditor rules. So it's possible to do that, and actually most companies will have kind of a mix of heuristics, and heuristics which are kind of rules of thumb associated with statistical rules. And I think that's kind of the way of the future, that you mix human expertise with statistical expertise, make them work together the best you can. And of course, very importantly, we learned that in some of our forensic type of studies, is that you keep incorporating more variables or more ways of thinking or more statistical evidence into what you are doing. Okay, there is this area called neural networks. Actually out of the book it says neural networks are attempts to make computers process information like human neurons. And that's not quite right. What the mathematical techniques that we use for neural networks are not really very, very similar to the storage medium of the brain and its information processing, which is more analogic than digital, and it really is more like a sensationalistic name for a statistical technique. Although this is a very good, interesting statistical technique, and the nice thing about neural networks and their technology, and there are a pile of algorithms that you use within neural networks, is that if you have evidence of the outcomes, so you have diagnosticity, or what we call also supervised learning, you can develop, without knowing too much, the relationships and underlying model that predicts the events to happen. The problem of this in many of the audit domains is that you don't have diagnosticity. You don't have outcomes in the past that you can compare with the evidence that you have. The human brain is a network of interconnected neurons acting like information switches. Think is the result of a particular flow of neuron switches. In a neural network, each switch is a mathematical equation that weights multiple types of input information. The end in the network is a final switch that collects information from previous neural switches and produces an output of neural network prediction. In general, in lay terms, what you have is something a little bit like a regression. What you have is a set of variables that you have measured and a set of outcomes. And you can do, for example, stock market. You have price of a particular stock and a certain things can determine those facts. And then you have this thing, you basically train your network. You basically run these algorithms that come up with what they call, is a prediction model, and there is this kind of hidden layer that tells you basically what parameters to use with the variable. And then you use these parameters to predict the outcome, etc. What are the strengths and drawbacks from neural networks? Neural network, the researcher just needs to feed in the raw information in the network. The data will pick out best functional form. We don't need to specify the specific form of the equation. So that's the hidden layer. It creates an equation for you. But neural network is not a panacea. It's impossible to figure out how an individual input is affected by predict outcome. The precise neural network for prediction is unknown. The multiplicity of estimate weighting parameters can lead to overfitting of the training data. There are fields that neural networks work much better than other fields. Now, let's talk a little bit about problems with supercrunchers. And recapping here a little bit again, we talked about regression, etc., etc., etc. Then we talked about randomization, and finally we talked about neural networks. And then we talked about a series of problems of evidence-based medicine. And basically what we're trying to say that evidence-based medicine is better medicine than just purely judgmental medicine. The other thing that we said here is that kind of trying to join statistical evidence and statistical models to human models might be the kind of a reasonable good compromise to improve what you do. And in general, my personal interpretation always have been, if you have no idea of what's going on and not a lot of data, you use human judges. When we started the project at AT&T, we really had no idea of what the underlying patterns of data was, and so we went to the auditors and went to the process owners and modeled what they were doing. A lot of the things that they were doing turned out to be reasonably consistent and reasonable things to be done. Very often in the statistical modeling you put variables in an equation or something like that. It's variables that you rationally think that would affect that particular phenomenon. You always worry if these variables correlate one with the other. However, the big changes that happened in our life in the last decade and a half is that businesses started collect huge amounts of data. When we did the work at AT&T, I left Columbia, went to AT&T, and this was 85. No one was doing data mining, or there are people doing that, not too many. And real-time information wasn't very common. But what happened at AT&T, and so it's not so serendipitous that this was at AT&T. At AT&T, since the mid-70s, the large electronic switches were collecting real-time information on telephone calls. And by the time I got in the mid-80s, they were doing some elementary studies of inbound calling, outbound calling, their business characteristics, etc. So by the time I got to AT&T Bell Labs, they had data in reasonably large quantity. Today we think it's pitiful amounts of data, but it was, they had 250 million phone calls a day, and they were collecting them with magnetic tapes, and they were processing, and they had embryonic databases there that could be used, and they were doing data mining, inbound and outbound analysis. So when that was happening and I was there, I thought, oh great, let's try to apply this into auditing. And so we had this very large billing system with a lot of transactions, and we said, how do we start this thing? And what we wanted to do at that time is collect anomaly evidence very close to the event, as opposed to waiting for a month or 2 months or 3 months. And at the end, after several years of work, we were reasonably successful creating systems that actually helped the billing operation substantially. But our first approach in the AT&T situation was getting the auditors to tell us what they were looking for. and creating algorithms that did that. It was easier there than it would have been anywhere else because they already had the databases built for other purposes, for a little bit of data mining and etc. And they had some of the tools available, and they wrote many of the tools. But this kind of age there, they had big data, they had big data, they had data analysis, they had statistical algorithms. This came into business more popularly, more frequently, more recently. And the fact that we have these large internet systems now collecting data automatically basically officialized, made this kind of technology much more popular. That's why today we talk so much about big data and we talk so much about data mining, et cetera, et cetera. Now, some purists think that by data mining, basically picking up data and trying to identify models that exist there, you are basically missing the serious thinking that you need to understand real-life phenomena. And instead of formulating your hypotheses and then testing them, you are actually developing empirical hypotheses, and you might have spurious correlation, might have all kinds of things. In reality, I think both ways actually go to the same direction, and we need to kind of work both with models that we don't know, and we try to infer the models out of pure data mining efforts, to things that human beings think there is a logic to it, and testing that logic, and then bringing those three things together. And that makes me mention two branches of statistics. One branch of statistics is the one that you all took in class. Basically, when we do hypothesis testing, we're doing a called confirmatory statistics. So you formulate a hypothesis that's a human being thinking and saying this is the way things are going to happen, and then you collect data to confirm or to negate that hypothesis. Now there is a whole branch of statistics that we call exploratory data analysis, EDA, that was very popular in the labs at the time I was there, and Tukey was basically the big originator of it, that basically said, you know, we look at the data we have and explore and try to understand what it says. And I actually personally think that EDA has been neglected, and EDA is a very, very useful branch of statistics. We should do it much more. And in reality, with this large data analysis, there is much more EDA going on, but we don't call it EDA. Now, back to the problems in super crunchers. Uniformity. Direct instruction teachers need to follow the most efficient way to teach their students without creative teaching. Epagogic predicts a movie's receipts based on primarily on characteristics of the script. It uses statistical formulas to tell the authors what to put in that script. Actually, that's very interesting, this idea whereby if sex, for example, draws a lot of attention, then you put sex in your script. If good food calls attention, you put good food in there. So you finish up with a mix of the things that are popular. And that's interesting. A little bit, sounds to me a little bit like denying certain aspects of creativity or denying a little bit of sophistication of audiences. Discrimination. Super crunchers may take a race of customers a factor when creating an algorithm for lending and insuring policies. Security problem. In May 2006, more than 17.5 million military veteran electronic records containing their social security numbers and birth dates were stolen from a government employee's computer. And I'm sure that you can tell stories of each one of these. Things are not uniform, things that has been used, computers for discrimination, you have lost data, and of course a lot of people are worried about governments that are totalitarian using monitoring and analytics basically to oppress their citizens. So obviously there are ethical and moral problems with a lot of these supercruncher data mining type of problems. And but you know, this is not different from any technology. Any technology, when the when there was guns developed. Guns could protect your population. The guns could also kill your population. Atomic bomb, the American presidents felt the atomic bomb was essential to protect the U.S. population before the Germans developed it. But of course, the atomic bomb can be used in very negative forms too. So that's the problem with any type of technology. All technology has a positive side and a negative side. There's a whole discussion about responsible use of science. In addition to uniformity, discrimination, security problem, privacy, with just a name, we can Google people on the fly to pull up addresses, photograph me at peers, etc. My wife pulled up my name, and there are pictures of her, pictures of her kids, etc., etc. She was furious about that. But what can you do, correct? Data quality. There are literally hundreds of data manipulation needs to be made in getting a large database shaped to run regression. Just to tell you a little bit of our experience, we tend to spend about half of the time of a project preparing the data. Actually, the analysis is the cream of the pie. And the difficult part is preparing the data, having the acquiring the data, preparing the data, and understanding the data before you do the fancy modeling. If a researcher makes a mistake in any one of the transformations, the bottom line prediction may be inaccurate. I talked to you about earlier about a finding in freak economics. Freak economics is a book by a guy called Levitt, professor of Chicago of economics, applied economics. And there he talked that guns in the house was 10 times less dangerous than having a swimming pool in the house. And that finding seems to be confirmed. But his most famous thing was the prediction of understanding the reasons for the decrease in crime in the United States, and particularly the decrease in crime in the city of New York and Chicago and et cetera, et cetera. And basically his theory was that because there were a couple of Supreme Court rulings that allowed abortion in the United States, because there was a substantial decrease on unwanted babies, those babies didn't grow up to be murderers or neglected babies and etc. That was his conclusion, and it created a lot of commotion. Actually, there is two of those books, Freak Economics and Freak Economics 2, and there's a lot of commotion of that, and obviously social discussions argued about that in every direction possible. Then there were some guys that decided to reanalyze his data and found out that he had made some serious mistakes in his data transformation, and actually the results didn't show significant results. Now, does that prove that he was wrong? Not really. Okay, it just proves that he didn't prove what he was saying. Just create hypothesis. But obviously this is actually a very interesting thing that, you know, if you transform the data too much. We have an example. We're working with a large bank, and they prepare the data for our predictive analytics studies. And we are having a hell of a time to replicate what we did analytically actually at the bank. We can't create that good results that we had. My opinion now is that they clean the data too much for us when we pick the data up and analyze. And we should have let much more of the idiosyncrasy of the data in place, and that would have allowed us to predict better. So you can't clean data too much. And so just kind of going back, uniformity, discrimination, security problem, privacy problem, data quality problem. And then there is this whole idea of hidden causes. Two groups are randomly selected to test if Weight Watchers plus financial to lose weight does better than Weight Watcher alone. So Weight Watcher plus giving them money. Some people after a while quit to response, which decrease accuracy of the result, because people who fail to lose weight are more likely to quit financial incentive group that's leading to a self-censored people with success. So there is an inherent bias on this thing. Wrong variable control. In a study to test if low-fat diet is good for your health, the low-fat diet recommended for the test group wasn't low-fat enough. So again, what are these problems? Uniformity, discrimination, security, privacy, data quality, hidden causes, wrong variable control. Now, does these problems invalidate the use of massive data or audit analytics? Of course not. Like human studies with human experts always have problems associated with it. You need to understand the nature of the problem you have, and you'll never really understand it totally correctly. Okay, let's just talk about competing with analytics. Now, the first part of this discussion was a discussion of what is these analytics that we use, what are the more elementaries, what are the biases that you have, and this comparison of human versus machine. Now, the next question we ask is it possible to do better than your competition using analytics? And intuitively, the response is obviously there are companies like Google, et cetera, that have collected data and dominated markets by collecting data. And you have histories in the past and expected in the future that will do that. But here we try to analyze a little bit better what are the characteristics of it. The capability varies by organization and industry and might involve supply chains, pricing and revenue management, customer service. At Netflix, the focus on analytics on predicting customer move preference. At Harris casino chain is the customer loyalty and service. Actually, Harris created this same kind of airline mileage concept. They created the casino mileage concept. And basically they created technology that you would put a card into the slot machines and they would know what you are doing. Very much in line with what we're talking about the hospital and etc. They were monitoring step by step what the client was doing and understanding the behavior of past clients. When do they stop gambling? When they gamble more? When do they get discouraged? They managed to change that behavior by creating mileage incentives, giving the client a free meal, giving the client entrance to a show, suggesting the client to use a different gambling medium, etc., etc., etc. And obviously the objective function of this gambling behavior stimulus was to make more money to Harris and to retain the client. And this has been very successful, and they actually copied that all over. There is a case, Harvard Business School case on Harris that you should see. Interestingly enough, the guy who did this analysis at Harris was an ex-Harvard Business School professor. He came to Harris, did the case, and then he was hired. He left Harvard, and he started being an executive vice president in Harris, developing these methodologies. Walmart, on the other hand, has very high quantitative methods of supply chain. And Rutgers, obviously, is one of the best department supply chain in the country, and we do a lot of looking at supply chain. We talked about basically distinctive capabilities, prediction of move preferences, loyalty, customer loyalty, supply chain. And basically what I said that a distinctive capability organization chooses would be supported by analytics. And of course you collect the data, create your algorithms with the things you want to emphasize. This area, there is this area called business intelligence. It's not very popular. Consultants talk about it all the time. And basically it entails capturing data and using this data for business purposes. And so this chart basically talks about the architecture for data and business intelligence. Management of data, transformation and processes, creating data repositories for what you want to use, analytical tools and applications, tools to show what you have, and then data about the data and operational process that generates this particular data. Companies today, large companies, basically contain their data in ERPs. And although some companies all operate out of one ERP, large companies have many ERPs. Sometimes they are all SAP, sometimes they are SAP and other companies and other types of enterprises or software together. And that creates a whole challenge of managing your data, extracting the data, and creating a view of the data. We have a couple of projects that we work on detecting duplicates, in particular in payment files. And the companies that we work with are supposed to provide us payables data. Turns out that the payables data doesn't come from one system, but comes from like 3 systems, one in the US, one in Europe, one in Asia, sometimes even more. And although people tell us when we start talking about duplicates that they don't have duplicates because SAP would capture all the duplicates, actually that's not a fact. Even SAP only would capture duplicates that are exactly the same, and human ingenuity allows for creating duplicates that look different, but they are the same. Control characters at the end of the name, etc., etc. We looked at a very large company's vendor files, and we found like 150 duplicate vendors. So, furthermore, sometimes we found in these different multiple vendor payments that certain vendors were being paid in 2 or 3 different systems, sometimes the same bill, same rent, etc., etc. So this whole idea of managing the data from operational systems is a challenge. And you don't detect this type of inter-system problems unless you analyze data on these systems. Now, in order to have data that you can analyze, you need to finish up preparing it in a set of repositories that have the data prepared for it. This ties up with the discussion we had before of data views, collecting data, and being able to use the data for analytical purposes, not cleaning data too much, etc., etc., etc. And then you have this whole area of analytical tools, and these are basically algorithms or methods that you use for exploring the data and exploring certain facts that you want to find out about the data. And finally, you have to display this to customers. Actually, I like much better separating this box into tools and applications of the tools, like models that you have developed. Because you shouldn't mix the tool like SAS, with a model developed in SAS. So I like better when we can put another pillar here, and the pillar is models that you develop. And once you develop the model and it extracts data, etc., you will have to present the data, and you might feed the data to other applications and call your attention to other things. What has been happening in the last decade in auditing is that a whole set of new forms of evidence in audit has appeared, and the standards have not dealt with it. So, for example, many companies now have real-time systems that spill out exceptions. And these exceptions are the same kind of thing that we did in the AT&T project. We call them alarms or alerts. These exceptions are basically sometimes aberrations that you don't really know what they are. Now, alerts are a new form of evidence. They are not the type of evidence that in a traditional audit you would do. But it should be incorporated in modern audit thinking. And actually, data analytics creates a series of new forms of evidence that have not been adopted in traditional audit practice. Now, talking about data management, data relevance, what data is needed to complete analytics, data sourcing, where can you get data being obtained? Actually, that should be sourcing. Data quantity, how much data you need. Data quality, how can the data be more accurate and valuable for analysis. Data governance, what rule and process are needed to manage data from creation to its retirement. Talk about data quality, how can data be made more accurate and valuable for analysis. Remember I mentioned before the idea of cleaning data. When we collect data from the project that we are working on and work that data to a certain degree, and let's say we come up with thousands of exceptions, we go to a partner that we work with, our client, and say we found this 1,000 type of things. And then they come back to us and say, well, you can exclude 2/3 of these because they are within the company transactions and there is no risk to them. So we create a little rule and pull them out. So that's preparing data. Now, sometimes we pull them out and we don't particularly like the idea of pulling them out. And so we have to put them in the background and start examining that data separately. So, you have to make a lot of judgments on what data you keep and what data you analyze. Now, other thing we had here is this transformation tools and processes, and that transformation procedure define the business logic that maps data from source to destination. Transformation entails standardizing data definitions, etc., etc. If you have 3 payables files, they come from different computer systems, they are not standardized. The definition are not standardized. And then there are different ways to store data, data warehouse, data mart, metadata repository. Actually, many companies now adopting what they call the audit data warehouse. And what is the audit data warehouse? It's basically a data warehouse which is prepared for auditors to use. Nothing particularly unusual about it. And these talks about some of the tools, analytical tools and applications. Spreadsheets, online analytical processes like OLAP, statistical quantitative algorithms, rule engines, data mining tools, text mining tools, simulation tools, and some other technologies, text categorization with text mining, genetic algorithms, stat systems, etc., 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 etc. Later in this course, we're going to talk about some of these technologies. And then there's a whole area of presentation tools, many of these items are items that are driving changes in analytics, the change of using data, and we are going to apply some of these into the audit domain. Then there is this whole area of human-driven changes. The growth of analytical competition will lead to a need for substantial greater numbers of people analytically oriented. And this is the reason why we are creating the certificate in audit analytics, because there has been a feeling in the audit profession, particularly, mainly in the public accounting profession, that our students don't know enough about analytics, and certainly after a few years in the profession, they don't have the competences for data manipulation, for analysis, for databases, and etc. And so we want to create and want to enrich the knowledge domain of auditors. As more firms' strategy-driven changes, as more firms become aware of the possibility of analytical competition, they push boundaries analytics in the products. And more analytical embedded in products, companies begin to analyze, report these knowledge assets. Strategic concern will drive firms to pay substantial attention to these methods. I also believe that the unique imprint of the large audit firms will be the audit methods that they are using, the analytics they use internally, and the apps, the audit apps that they apply in their work. We started this discussion, mentioned the word big data, and you all seen big data mentioned in the press, mentioned in newspapers, etc., etc. Let's just talk a little bit about that. I primarily base this discussion out of some McKinsey work because they are very good at selling their work. So we'll talk about McKinsey. It's not just about big data. For big players in the enterprise technology, algorithm is about finding a big patterns beyond the data itself. And obviously you have the data, and you look inside the data to see what it is telling you. The exposure of online life and cheap computer hardware have made it possible to store immense amounts of unstructured information, like emails, internet clickstreams, and the search of stored information to find something that can be explained. The real trick is to do this cost efficiently. Companies doing this at large scale look for similarities between one field and another, hoping the common means of analysis. Now, in general, remember I mentioned to you two types of statistics. One type is complementary statistics, the other type is exploratory data analysis. Actually, they kind of intersect. And when you are looking at big data, you typically are looking for something, and you typically have some theory that you are trying to detect. In the last 5 years, IBM has spent some $14 billion purchasing analytic companies in the several big data initiatives to look for adjacencies between one business and another. IBM became probably the largest player in the United States in analyzing for Medicaid, Medicare data, and they have in there an engine with thousands of rules based out of observation. The trend of looking for commonalities and overlapping interests emerging in many parts of what IBM business. At the ultra-small nanoscale examination of cell, researchers say the discipline biology, chemistry, and physics begin to collapse into each other. In a broader search for patterns, students of the computing language, known as R, have used methods to counting algae blooms to prove pattern genocide against native people in Central America. Online marketeers look at your behavior in a number of contexts to sell you something. While it is attractive to contemplate the way everything may become connected to everything, it presents a number of large challenges. I'm just talking about using R. In our work, we actually use a whole set, like Wake and R, for research. We also use live physical packages like SAS, and we also use audit packages like ACL and IDEA for doing the different analysis. And sometimes the decision of what software you use to build applications has to do with what the partner has. Other times it's what's cheaper to do. Other times what we have computing capability to apply. The lab research method had been important for a century in both scientific advance and product development. Soon it may also accommodate a search for truth based only on pattern spotting. Near term, companies will have to make tough choices about where to invest and which signals to watch. Trying to do everything will still amount to doing nothing. Now, McKinsey. Radical customization, constant experimentation, and novel business models will be new hallmarks of competition as companies capture and analyze huge volumes of data. If companies are capturing and analyzing huge volumes of data, auditors will have to do the same. And if auditors only use summarized data to do their analysis, they are going to have to find ways to validate that the large data was summarized correctly. The top marketing executive at a sizable U.S. retailer recently found herself perplexed by the sales report she was getting. A major competitor was steadily gaining market share across a range of profitable segments. Despite the counterpunch that combined online promotion merchandise, the company kept losing ground. When the executive convened a group of senior leaders to dig into the competitor's practice, they found that the challenge ran deeper than they had imagined. The competitor had made massive investment in its ability to collect, integrate, and analyze data from each store and every sales unit, and had used this ability to run a myriad real-time world experiments. What did they do is they tried different strategies in different stores in real time, and analyze the results out of that. At the same time, it has linked this information to supplier's database, make it possible to adjust prices real time, to reorder hot-selling items automatically, and to ship items from store to store easily. By constantly testing, bundling, synthesizing, and making information instantly available across the organization, from the store floor to the CFO's office, the rival company has become a different, far nimbler type of business. This actually applies also to the auditing domain. We need to be constantly changing the models that we use and trying to enrich our databases of potential problems in audit and create analytic methods to support it. McKinsey, are you ready for the era of big data? What happens in a world of radical transparency with data widely available? If you could test all your decisions, how would that change the way you compete? How would your business change if you use big data for widespread real-time customization? How can big data augment, even replace management? Could you create a new business model based on data? First, did we really have increased transparency? Can other companies know what a company is doing more than before? Yes, they can. Traffic to a business is a very good proxy for the amount of business that they do. Like foot traffic wasn't before. If you could test all your decisions, how would you change the way you compete? Now you have all this randomization, etc. they can do. How would your business change if you use big data for widespread real-time customization? I would like to the question, how would change auditing if you use big data for widespread real-time customization? How can big data augment or even replace management? We ask the question, how can you automate the audit using audit apps? Could you create a new business model based on data? Could auditors create a new business model based on data? And they are inevitably going to have to do that because the old model of measuring labor hours and charging from them is kind of basically obsolete. Now, McKinsey has this very cute chart here. The ease of capturing big data value and the magnitude of its potential across sectors. And this is ease of capture, very easy to capture there, very difficult to capture data, and potential value index. So where they have the highest, that's easier to capture and the highest value is in the information industry and the finance insurances. So this is our industry here. Now, administrative service, construction, etc., is a much lower potential area for using big data. So this is where we are, and this is where we need to invest. Okay, finishing up, let's talk a little bit about competing in analytics, and then we'll finish up just applying slightly to auditing. The David report proposes 4 areas of competing in analytics. Decision capabilities, enterprise approach, senior management committing, large-scale ambitions. And then they create this kind of maturity model where companies are progressively more analytical. And this is misspelled, should be competitive. This is the 2 books that I mentioned to you before. The pictures, Davenport and Harris, and the Ian Ayers book. Okay, I just put a couple more slides together here to just kind of give you an example, an illustration, a discussion a little bit about where we are going with audit analytics. Many companies, particularly public account companies, have been now doing substantial analysis of general ledgers. As a little postscript here to our discussion, the AICPA, which is Assurance Service Executive Committee, is developing a thing that they call the Audit Data Standard. And the idea behind the Audit Data Standard is that in the past it has been identified that the greatest problem that internal and external auditors have is getting the data they need from the IT systems of the company because of the complexity, because of the low priority of audits, and because maybe a natural desire by auditees to obfuscate auditors. That has been a major problem. I started teaching IT audit over 30 years ago. I thought, well, everyone is going to be an IT auditor, and a lot of these current manual functions have been obsoleted. And actually, we continue sampling, we continue doing a lot of manual stuff. And that's basically because data is not available. So the Center for Audit Quality initially, and now the AICPA is creating, and now is in exposure draft, these standards for data to be supplied to the auditor. At this moment, we have the general ledger standard and we have the payable standard being proposed and is being discussed. There are comments coming out and etc. Associated with this idea is an audit data standard whereby a standard audit file will be available to every auditor, external and internal. There is also this idea of audit apps, whereby you're going to develop little scripts depending on the language you're using or the software that you're using that you can apply into your audit program. And progressively there'll be more and more and more these audit apps and scripts that you can apply to this audit data standard, and you'll be able to automate a large part of your audits. And one of the things will be testing general ledger. And in the past has been already required to testing general ledger. These general ledger tests run for almost every audit. Additionally, and fairly simple tests are added by each audit team as a holistic or against audit expectation. And we want to kind of systematize this, think about this in the several different areas. And these combinations of areas will provide additional value in the audit process and automate a good part of the audit test. Things that you can do is test duplicate entries. You can test for large transactions, but you don't need to do. You stratify, look at what accounts are impacted, look at which users use most posting resources. Now, just looking at these kind of description of GL tests, they're all little tests looking for something that you manually would do. And eventually you'll be able to look for something that you manually wouldn't do, that is aggregation of large amounts of data or patterns that you couldn't really manually do except by just kind of guessing a pattern. Now, to conclude this discussion, we started originally talking about the predictive audit. We talked about the retroactive audit, the predictive audit, the proactive audit, and I just want to discuss a little bit that kind of thing. This is a project that we did in which we combined forensic analysis and real-time technology. We had a particular process that was a wire payment process, and we had about 250,000 transactions. And by multiple analysis of those transactions, we came out with certain filtering rules that would call our attention to potentially fraudulent type of transactions or erroneous type of transactions. This was done by the traditional forensic technology, so statistics and modeling and et cetera, the wire transfer operation created archives. We analyzed the archives and came out with forensic analysis, and this forensic analysis led to a set of forensic models that resulted in one dissertation that would predict, that would extract out of the data that we had fallacious transactions. Now, the predictive audit approach would be that you would apply this data that you receive, you filter by forensic models. The traditional approach, you would basically expose factor fails by forensic models. The new approach is you propose a particular wire transfer, you examine by forensic model, and if it gets a high loading factor of potential problem, you stop the transaction and don't execute it. And examine it, and then you finish up executing it.
At the same time, you continue developing additional forensic models because data with time and with new characteristics change in nature and you need to be continuing analysis. But this particular idea is what we call the preventive audit, whereby you stop transactions that are fallacious before they happen. Okay, and this kind of summarizes a lot of our discussion because it talks about the different elements of the predictive audit model that is also in the big data story. Understand what you're analyzing, capture the relevant data, take out the things that are irrelevant or there are defects that you know that are not really defectors. Create some indexes that will tell you in general what things are happening, KPIs, key performance indicators, and extraction models. Run the models in different scenarios. Examine the exceptions, and I say it on an interactive basis because you keep adjusting your models by extracting the stuff that you don't think is dangerous or that you really won't pay attention, or that your partner tells you not to look at them for one reason or the other. And then you decide on what in this hierarchy discriminant function on these are very dangerous transactions, which are less dangerous transactions, where do you cut off? And that's deciding on the profile risk. And then once you have that set of decisions, you place filters in the end of the process, create an audit by exception mechanism. If something exceeds that coefficient of risk, examine it. Create interfaces between managed continuous monitoring and audit by exceptions, and continue developing your forensic model. Now, a final comment around this is many people of traditional audit nature wouldn't consider this auditing. They would consider this controls. They would consider this work of management. And of course, there's this big distinction that is constantly being discussed these days: what is continuous monitoring, what is continuous auditing. And I usually don't think that discussion being particularly useful, but I usually say continuous monitoring is done by management, continuous auditing is done by auditors. You can't do continuous auditing without doing certain degree of continuous monitoring, but you don't have to monitor every variable that an operational manager will do. So that's kind of the big discussion. Now, if with analytics and data technologies having come to place, we can do very different things to assure integrity of data and to decrease the amount of losses that the company has for fallacious transactions, which include errors and irregularities. You can do that. Traditional audit didn't have these capabilities, so the way they defined independence, materiality, etc., 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 was with the old world view. The new world view allows you to stop transactions before they happen, and this is kind of an audit activity, kind of not. I think the audit of the future, the predictive audit, will incorporate dramatical changes on what's included, and I do think that filtering and blocking and forensic modeling, etc., are all part of this future data quality assurance world. And I just want to read you a couple of comments out of KPMG's article called Continuous Audit, Continuous Monitoring, Preventing Care Against Fraud. CACM shifts management and the internal audit department focus and reviews from a traditional retrospective data approach to a proactive preventive stance. Many indicators of fraud and misconduct, both action potential, reside within organization financial operation, transaction data can be identified using forensic-based CACM tools and techniques. These include sophisticated analytic tech, computer-based cross-matching, and non-obvious relationship identification to highlight potential fraud and misconduct. So, finishing up, we started by looking at these articles or these books on large data. And what we talked about that First is by the idea of human judgment versus modeling, and we concluded that human judgment doesn't do as well as modeling. And we found a lot of restrictions of things whereby modeling might bias, might create privacy concerns, etc., etc. But in general, human models are not as good. Human judgments are not as good as machine models. Then we discussed a little bit the application of certain models, in particular the regression model, and we had this baseball example, and we had the wines example, and then we had a lot of evidence-based medicine examples, all of them explaining approximately how first you put statistics in the judgment, and then where you put data, and then you share data in hospital judgments, and et cetera, et cetera. So we put that whole story together. We talked a bit about randomization in experiment, and the basically big message here around this was we're collecting much more data than before, and we have to use this data intermittently, but very importantly in decision making and in assurance. I interspersed the discussion with some examples in the audit arena out of our work. And then we talked a little bit about the challenges of big data per se and the strategic advantages of big data. And we concluded by talking a little bit about the predictive audit, in particular developing a forensic model that uses it as a preventive mechanism, and even kind of the challenges of rethinking what the concept of assurance is. Thank you very much.